Hello and good morning everybody. Today I will talk about spectral descriptors. As you maybe know, we are using spectral descriptors as the basis for many calculations within ImageLab, and I just try to give you some background ideas and some motivational arguments why to use spectral descriptors instead of raw intensities as it is commonly done by many other imaging products. First of all, I just want to show you a very old slide which I have calculated many years ago, and then we had the question whether it's a good idea to use spectral descriptors or spectral features, as it is sometimes called, instead of raw data. And the setup of this experiment was to use either spectral descriptors or raw data, creating a classifier by adding several features, and the feature selection was done in this case by a simple approach called forward selection. And as you can see here, building up a classifier using raw data takes many features in order to get a classifier which is good. In this case, it takes hundreds of features in order to get up where the classifier is when you're using spectral features. So using, for example, 4 or 5 spectral features creates a classifier which is almost perfect, and this quality criterion here is a logarithmic measure. So you see that using spectral features tremendously speeds up the build of a classifier, or on the other hand, if you have a constant and fixed number of spectral features or raw data to use, then you immediately see that using a fixed number of features creates a much better classifier in the case you are using features instead of raw data. So after having discussed the relationship of spectral features and raw data, I just want to show you a few spectral descriptors as they are implemented in ImageLab. And of course the most simple descriptor would be just to use raw intensities. Those raw intensities can also be calculated by using a reference value. And for example, you could define a level which is calculated from a reference point, and the difference between this level and the peak height is the spectral descriptor. Or for example, you could create and calculate a baseline and use the difference between the peak height and the intersection of this marker with the baseline as the spectral descriptor. Of course, if you just take the reference point as the intersection of this marker with the signal line, then the exact location of this reference point is prone to noise in the data. So what we implemented is that we just define a region of neighborhood, and within that region, which normally 5, 6 or maybe 10 points, and within that region the signal values are averaged, and the average y value is used as the baseline reference point. And the same is done here. So by averaging those signal levels, you get a more stable reference point and of course a more stable baseline. Besides the intensities, ImageLab also supports the ratio of intensities. So you can just specify 2 wave numbers, for example this one and this one, and calculate the ratio of the raw intensities of those 2 peaks. Of course, there's a small problem. If the denominator of this equation just approaches 0, then the ratio would just explode towards infinity, and in order to avoid this, we just implemented the logarithm of this ratio, which is much nicer, especially if you are plotting this in an image. Of course, again, you could not only use the ratio of raw intensities, but also the ratio of intensities obtained by subtracting the peak height from some baseline reference. It could be a constant level, or it could be a baseline which is calculated again from reference points. In this case, the reference points can be set by the B markers, B1 and B2, and the markers A1 and A2 define the location of the peaks. Another kind of spectral descriptors are peak areas, and again we offer here three kinds of peak areas. The peak area obtained by integrating just the raw data between two markers. So this is the area between marker B1 and B2. And of course this is not always a good idea, because you are integrating the signal baseline as well. So maybe you would want just to create again a reference level and integrate the difference between the signal and this reference level. If you define a baseline by specifying two reference points, then the area of this peak is just taken above this baseline. And another kind of descriptor is a ratio of peak areas. You could define two areas, the left one and the right one, and the areas of those two regions are again calculated by putting them into a ratio and drawing the logarithm of it. And of course you could again define a baseline so that slopes in the signal won't affect the resulting peak area ratios too much. Quite interesting descriptor is the position of the centroid. The centroid is calculated within the two markers B1 and B2, and the red line here is indicating the centroid, and the spectral descriptor, the variable which is finally going into the data analysis, is just calculated as a relative position of the centroid in relation to the entire interval between B2 and B1. So if the peak just shifts for some reason, then the centroid will shift, and of course this quotient as defined here will change, and this spectral descriptor can change between 0 and 1, as it's obvious from this formula. Currently the most interesting spectral descriptor, which is quite powerful, is the correlation with a template peak. The idea is quite simple. You define a template spectrum which contains a triangular peak, so the entire spectrum, this is this blue-green line here, the entire spectrum is 0 except for the region where this template peak is defined. So within that region there is a triangular peak which just starts at the marker B1, goes up to the marker A1 and goes down again to the 0 line at the marker B2. And this triangular peak is then correlated to the signal, and the correlation is multiplied by the peak height, and if the correlation is negative or not significant at the level of significance of 1%, then the entire spectral descriptor is set to 0. So in effect, using this spectral descriptor, we can just isolate individual peaks within a spectrum and in parallel reducing the noise in the spectrum considerably. So in order to give you an idea how spectral descriptors work and what is the effect of using spectral descriptors, I just want to switch over to another PowerPoint presentation which tries to show you how spectral descriptors influence classifications, for example. So let's assume that we have a set of data which is within this ellipsoidic region, and another set of data which is outside. So if I just try to find a simple linear classifier, as it is commonly done, for example, by linear discriminant analysis, then you have no chance to create a classifier which can distinguish between the inner class 1 and the outer class 2. So what we can do is, as we know that this is an ellipsoid, we could just perform a transformation which is guided by the idea that the data are bounded by an ellipsoid. So as you know, an ellipsoid is just controlled by the focus 1 and focus 2 and a constant sum of L1 and L2. And if we just transform the xy coordinate system, which we just used before, into a new coordinate system which is based on L1, L2, then the elliptic region will be transformed in a rectangular region, and all the data points within the elliptic region will be inside this rectangle, and all the other data points outside will be in this open rectangular region, which is open in this direction, and the other part of the new space is just empty. And what you can immediately see is that a linear discriminant classifier is sufficient to distinguish between points within the ellipsoid or outside the ellipsoid. So this is a very clear example that by transforming the data space we get more simple data structures, and these simple data structures also, of course, support the quality of, for example, classifiers or any other kind of models. So let's have a very simple and quick example. Therefore I'm loading a set of descriptors which I just defined previously, and I will show you the effect of such descriptors. So let's first of all have a look at the very simple descriptor, which is nothing else but the intensity at a single wavelength. So if we are just looking at the wavelength 2927 wave numbers, you see here an image, and what you see here is that there is some spot, and this spot is clearly indicated by a peak in the region around 3000 wave numbers. And now the idea is, of course, if you're just looking at a descriptor which is just a single intensity, then you get some fake image parts here, and those fake image parts just come from the fact that the entire image is rather noisy, and there are some noisy parts which are on the average above 0, and so you get a contribution to the image at this point. So you know, if you just struggle with noise, you could, for example, use an integral. So just creating the integral, comparing it with the raw data you see here, using the integral creates a much smoother image. And of course the integral is the reason why this image is smoother, because the integration removes part of the noise in the data. But there are some fake peaks or fake spots which are maybe just spots which happened to be created simply from the fact that the noisy data is just on the average not 0. And as you see here in this particular tiny spot, you get here noisy data, but the average of these noisy data points is around 100, and of course this creates a spot, because only those parts which are zeroing out will create zero levels. And of course this spot is clearly visible, and now the idea is, if we can introduce chemical knowledge, then it could get much better. And the idea is, as we know, organic substances, and especially aromatic organic substances, create peaks around or below 3000 wave numbers, and so we could just create a new spectral descriptor, which is nothing else but the correlation with a template peak. And this template peak is a simple triangular peak. You have a baseline here, then the triangular peak goes up to the maximum, goes down to the zero line, and then stays at zero. And if you create the correlation of this template spectrum, which contains this single triangular peak, and you plot the correlation, then you get an image which immediately shows a very clear picture and shows you that there is really only one spot which shows this aromatic peak. And if, for example, we just take this image and copy it on top of the image stack, then you immediately see that this brown spot here, which is has been copied from the descriptor editor and blended with a microscopic image. You see here the microscopic image, and this spot is different from the other particles on this image, and it's clearly an indication that this spot is some kind of an organic droplet, maybe some oil droplet or something like this. And you see here that the selectivity of the spectral descriptor is quite high, and this is the natural explanation that if you're using spectral descriptors, you're getting better selectivity, you're getting less noise, and altogether the performance of your models will increase. Finally, just let's summarize the benefits and the disadvantages of spectral descriptors. Let's switch over to a PowerPoint slide. The benefits of spectral descriptors are, of course, as you have seen, the introduction of chemical knowledge. Due to the fact that you are using a smaller number of spectral descriptors, the data spaces are much smaller, and the data structure may become simpler, and in many cases, so at least in 90% of the cases, they're actually becoming simpler. This reduces the required time to perform the calculations, and, which is quite important, spectral descriptors are reducing noise in the data in many cases. Of course, there are some disadvantages, and one of the disadvantages which you can immediately see is that you have to put in extra efforts to set up spectral descriptors. And of course, there is one problem: if you are not creating a full set of spectral descriptors, then there is some chance that important features of an image might be overlooked. But there are some strategies to overcome this limitation. So I hope my presentation gave you a quick overview on spectral descriptors, and if you have some questions or if you need some further information, just drop me a mail to hans@epina.at. Well, thank you for your attention, and I hope that we will meet again when we are discussing the next part of ImageLab.